So thank you all for coming to Beyond Shuffling. I'm Holden, and the cute bunny is a plushy bunny, and her name is Bun Bun. And my dog over here is named Boo, Boo the dog. So I'm Holden. My pronouns are she or her. It's tattooed on my wrist in case you forget. Just check that. I'm a principal engineer at IBM's Spark Technology Center in San Francisco. So if I fall asleep in the middle of my talk, just poke me back awake. I'm a little jet lagged. And my boss asked me to say that IBM is a founding member of the Scala Center as well. And we're really excited with all of the really cool things that are happening around the Scala Center and Spark, and sort of how we can be involved with some of that and bringing a lot of the cool stuff that's happening in Scala and helping that go with Spark. Previously, I've been at Alpine, Databricks, Google, Foursquare, and Amazon, doing sort of a mixture of big data and search and recommendation problems. I'm a co-author of the Learning Spark book, and to get people to actually ask questions, the first person who asks me a question at the end of the talk will get the English version of Learning Spark. It's a little out of date, but it's fun. If you want to follow me on Twitter, you can go right ahead. It's mostly pictures of stuffed animals and random complaints about programming languages. Occasionally, stuff about Spark is thrown in for good measure. I've got a slide share. Slides from today's talk and most of my previous talks will be up on SlideShare. If you want to follow me on GitHub, there's a bunch of random Spark-related projects. And I also have videos from a lot of my other Spark talks. They're up there as well. And I'll probably throw out some references to them, too. So I'm going to start with sort of what my assumptions are about you all as people. And if I get a lot of really blank faces, we'll switch things up a bit as we go. But we'll talk about sort of how to reuse our data in Spark efficiently, considerations for when we're working with key value data, and sort of what key skew means for working in Spark. We'll also look at how Spark SQL can help us make really fast Spark programs. It's really great. Then we'll also talk about sort of iterator to iterator transformations inside of map partitions. And I'm briefly going to talk about how to test Spark code and sort of how to validate your Spark code. And sort of this sort of leads into some of the counters and stuff that Spark collects on our job as we're running. That can be useful in just general debugging as well as testing and validation. Or if you zoned out, you can just think of us as going from this very sad kind of angry cat that's wet to this very happy unicorn. We're going to go from ooms to the happy Spark land, where there are no out-of-memory exceptions. And it's a very happy place. So I'm hoping you're all nice people, and you don't mind pictures of cats. And you may or may not like pictures of David Hasselhoff. How many people like pictures of David Hasselhoff? OK, some people. That's good. I promise at least one picture of David Hasselhoff and lots of pictures of cats. The more serious one is, how many people know or have worked in Apache Spark? Like you wonderful. OK, this is very good. How many people want to scale their Spark jobs? You want to make things go faster or handle larger data sets? Is that also? OK, great. So you did come to the right talk. That's wonderful. And I'm hoping you don't mind a grab bag of topics. At this point, though, really, that's probably not going to change. You're sort of stuck with it. We're going to be focused mostly just on core Spark, as well as sort of the SQL and data frames and data sets that are now in Spark 1.6. This doesn't really dive deeply into streaming or machine learning or any of the really sort of application-specific libraries that are built on Spark. If you're interested in those things, there's some other great talks that I can recommend. So that's sort of my pitch for you to stay for the rest of the talk and not go and get coffee, that this cat very much wants to go and get some coffee. But it's OK. I'll understand if you want to leave in the middle to get coffee. I'm going to take some breaks to get coffee myself. So we're going to start with the really standard example. And this example looks pretty reasonable, just like presumably how this file cabinet looked to that cat. It looked pretty reasonable and safe. But in reality, it's actually pretty bad, right? We've got our really standard word count example. done wrong, but it's there and it looks OK. And then we also have another one where we're looking for all of the error messages in our input data. And so this is, a really basic, common thing that we would do, and it looks pretty reasonable in this code, right? Like, unless you're explicitly looking for it, it probably looks like this code is reasonable. And the thing is, it will actually probably run successfully. It's just we could do this a lot better. So let's look at some of those things we could do. The first is we have the same input data that we're using multiple times, and we haven't explicitly cached our input data. And this is important. Spark's lazy evaluation is really great because it lets us build up this really cool graph, and then Spark is able to do a lot of really cool optimizations using this graph. But the sort of downside of this approach is that it only gets to understand our program up to the point where we have an action. And our action is something like saving it out to disk or counting the records, something that forces Spark to evaluate it. And Spark can't see forward in our program to tell if we're going to be reusing the same data multiple times, right? It's not like a compiler. It doesn't have a whole program view of what's going on. So we need to help Spark out, and we need to tell it when we're going to be using data multiple times. And so there's a few different options to do this, right? We can cache it in memory, and that's really good. If your data is pretty small, caching in memory is fine. If your data is bigger, you might want to just cache it in memory and fall back to disk when you fall, if there's too much contention. And this can get a bit tricky if you're running in a shared environment. So if you were in a notebook environment like Databricks Cloud, and you have a bunch of people on the same context, the data that you cache could actually be evicted by other people's caching actions. And this can lead to sort of wonky performance, which doesn't really make sense unless you go and look at the cache page. How many people run on a shared cluster? You're not the only people on your cluster. OK, so most people here are very lucky or have very big budgets, and that's awesome. That's great. For the people that aren't on those dedicated clusters, one thing that can happen is you can get your jobs evicted. And this is just sort of a fact of life of working in a shared cluster. And it's not the end of the world, because Spark is resilient, right? It's very easy. It's very capable of handling our evictions. But the problem is the evictions intermixed with the caching can give us some really bad performance. And mostly what this happens is if we lose like half of our executors, there's no way the cache data that we've cached on those machines is actually going to be there, right? Like, we've lost so many machines, we are going to have to recompute our data, and that's just a thing. If you're on a noisy cluster, it might be worth it to checkpoint your data. And checkpointing is a really sort of heavy-handed operation, right? It's sort of the MapReduce model, where you take your data and you write it out to HDFS or whatever persistent storage system that you're using, and then you go from there. And this way, even if you lose half your cluster, you aren't going to have to recompute the data. And it's not like the recomputing the data is something that you have to do. Spark will do it for you, but it will slow down your job. So checkpointing can be useful for people in shared contentious cluster environments. But if you do checkpoint, always persist first, because otherwise checkpointing is really designed for the situation where your lineage graph has gotten really, really large, like you've done a whole bunch of transformations. And so checkpointing will actually throw out this lineage graph, and it'll also not bother keeping the data around in memory. So as soon as you checkpoint, it actually just writes it out to disk and gets rid of everything. And that's probably not what you want. You probably actually want to write it out to disk, but keep it in memory and just fall back to the thing that's in HDFS in case you lose your clusters. Or, sorry, lose your nodes in your cluster. The other thing with which we were doing in our word count example is groupByKey. And groupByKey is pretty much the devil. And this can happen. GroupByKey can be safe if we have like absolutely no key skew and most of our keys are unique, right? In that case, GroupByKey is pretty reasonable. But I think for people coming from an engineering background, we're not always used to thinking what the distribution of the data that we're processing looks like. For people coming from a data engineering or a data science background, you're maybe more used to sort of having that mental model. But there's a really good chance that even if you think you don't have key skew, after you've transformed your data a few times, you may have accidentally brought like a null value in as one of your keys, and then you're going to end up with this giant amount of key skew. So yeah, so why do we care? So when our keys aren't evenly distributed, groupByKey will explode. But that's not really all that hard to make happen. Like, we can make groupByKey explode in a lot of perfectly reasonable situations. But even if we don't have the situation where something explodes, if we have key skew, we can really easily get into the situation where we have unbalanced partitions, or we end up with a partition which is beyond the partition limit in the shuffle of 2 gigs. Or even if that doesn't fail, the uneven sharding will give us stragglers. So we'll end up with some machines which just have to process so much more data that they take twice as long as the rest of our jobs. So groupByKey is pretty evil, just like this cat. Yeah, pretty evil. And what it does is it groups all of the records with the same key into a single record, even if right afterwards we perform some type of reduction, right? So a pretty common pattern is to group your data together and then compute some sort of summary statistic on your group data. If we're in SQL, everything's OK. When you group your data together in SQL, it actually delays the computation and actually waits to see what you're doing. But in regular Spark on RDDs, when you group your data together with groupByKey, it doesn't have that ability to see what you're doing next. So it ends up looking like this, and it's very sad. And our cat gets quite wet. And our record is clearly too big to fit on a single machine. And for people that are wondering, this fake sample data, I like to pretend is handlebar mustaches ordered by zip code, and 94110 is the hipster zip code in the city that I'm from. So it has too many handlebar mustaches to fit on a single machine. So the correct way, so I mean, this is the bad way, sorry. This is groupByKey word count. And the actual normal way to do it is to just do this really simple reduce by key, right? And when we do reduce by key, Spark is actually able to go and do sort of a map side reduction. And that's pretty awesome. So essentially, before it even begins to transfer data over the network, it's able to reduce the data locally and then transfer only the reduced data over the network. And then even then, it doesn't have to create these giant records, even if the map side reduction doesn't give us anything. So this is a really simple example of groupByKey on some Python files. It's kilobytes of data because I actually wanted the job to succeed. But if you were working on real data, you could just replace the K with a G or a T, and it would be exactly the same thing. And we can see it has a shuffled read of 48 kilobytes. And if we did reduce by key, we'd actually just have a shuffled read of only 11 kilobytes. And that's a pretty big difference. So as a general rule, if you find yourself working in Spark and you find yourself writing a group by key followed by a map values, there's a really good chance that you want to be using reduce by key or aggregate by key. You get a free map side reduction, and as a benefit, your job doesn't explode, which is pretty awesome. And you get to be happy like this cat inside of some bread. But there is a catch, right? Like, group by key can be safe some of the time. It's not like just there to make your life miserable. If you really truly have mostly unique keys, it's pretty safe, right? So you can do this if you did the README. If you read in something where most of the words were unique and then did group by key, it would be OK, right? And this can actually, I think this is part of what makes group by key kind of the devil, is it looks OK in our sample test data, but once we start throwing it at actual real-world problems where we have missing values, that's when it starts to actually explode. Well, we can get explosions with key skew without having to use group by key, right? Just shuffling our data can cause the problem. So if we return to our handlebar mustache example, and we just want to sort this data, this can be pretty bad, right? So while our records are still individually quite small, Spark isn't able to do the split intelligently because the key is the same. And when we need to sort, Spark just isn't able to split if the key isn't changing. So if you have all of your records with one key, and here it's the mission, but there's a very good chance that your one key that has all of the records is going to be null, at least in 80% of the data sets I've worked with. You're still going to have really bad performance even if it succeeds. So we can just add some junk to the end of our key, and it's really simple, and it lets Spark do intelligent splitting. And it's actually quite smart, right? Like Spark samples the data for us and actually comes up with a reasonable set of splits when we sort our data, which actually, incidentally, means that sort by key is like this kind of weird quasi-transformation, quasi-action, because it actually samples your data, and that involves forcing a computation of your data, and then it actually does its actual shuffle after that. So the traditional transformation action dichotomy isn't quite as clear as it's necessarily made out to be in all of the books. But yeah, so we can just add some junk to our key, and it works pretty well. And actually, here's our first David Hasselhoff in the top corner, I think, or at least what Google Images told me was David Hasselhoff. And we've got some fire too for good measure. So their shuffle actually has a bit of cool magic inside of it. And it's sort of an artifact of the way how the shuffle is implemented in Spark. When we shuffle our data, Spark actually creates these temporary shuffle files. And now, I mean, when you hear temporary files, you don't normally think awesome performance. You normally think really shitty performance. And in general, that's actually probably true. But for the shuffle files, they tend to actually just stay in the OS page cache because they're not all that big. But we can actually reuse the shuffle files. So if we have some really complex shuffle, we don't need to explicitly cache our data at that point, right? If we just keep that RDD around, we can continue to reuse that RDD shuffle files. And this gives us a pretty similar performance characteristic to as if we had cached it to disk. So this can actually be quite good. The only sort of downside of this is these shuffle files aren't really intelligently managed. So Spark's caching is quite smart, right? It uses the pretty standard LRU caching algorithm. But for shuffle files, it just leaves them there until the garbage collection on your driver program is triggered. And if your driver program has a whole bunch of memory assigned to it, that really bears no relationship to the amount of disk space that you have on your workers. So one of the things which you might find yourself encountering if you start keeping a whole bunch of RDD references around is that you've got all of these shuffle files, and you need to clean them up. And you can do this by triggering a GC event on your worker program, just manually triggering the GC event. Or if you feel like using Spark's internal APIs and lying about being inside of package org Apache Spark, there's another way to clean up shuffle files in there. But it'll probably change in between each version, so be prepared to rewrite your code several times. You probably don't want to do that. You probably just want to trigger a GC event. It's much easier. So, more cats. So iterator to iterator transformations. So how many people use map partitions? OK, cool, a good number of people. So map partitions is really great. It gives us a lot of control. And this is really useful if we're doing things like setting up database connections or essentially just doing crazy things inside of our Spark jobs, right? Like maybe we're making a PRNG for each partition, or we're doing something a little outside of the norm, right? The one problem with map partitions is that it also trusts us to not be idiots. And when people trust me not to be an idiot, that's normally when my code fails, because I'm not super attentive. The default transformations are actually implemented using the mapped partitions RDD, so map, filter, flat map. Many of these are implemented using the same RDD that map partitions is in. But if we accidentally implicitly convert our iterator into a list or really pretty much anything, we can force Spark to load our entire partition into memory. And then we've also made it so that Spark can't spill to disk as it's processing the partition. And this is unfortunate because sometimes you actually want to process more data per partition than is reasonable to hold in memory, right? You actually want to be able to spill the disk as you're going. So when you're using map partitions, it's really important to be careful that you don't implicitly or otherwise convert your iterator into something which forces Spark to keep it in memory. So the TLDR, and here's our second David Hasselhoff, at least I think. This is what Google Images told me, doing the splits. The TLDR is be careful when you're using map partitions, because it can explode, and then you'll have to do the splits in front of a fiery building. Yeah. Sorry for the David Hasselhoff jokes. It seems like there's 2 people that like them. Well, maybe 3, because I like them. OK, sorry. We're going to move on to Spark SQL, which has decidedly less David Hasselhoff. But how many people are actually already using data frames or data sets? OK, cool. That's a good percentage. For those of you that aren't already using data frames or data sets, I'm going to go into saleswoman mode, even though I receive $0 for getting you to use Spark SQL. But I think you really should be considering it. If you're OK with some of the constraints that Spark SQL provides, it gives you a whole bunch of power for free. It gives you really super fast serializers. And not only are the serializers fast, they're also more space efficient. The results are much more compact. And the serialized values can even have certain operations performed directly on the serialized values. So if you remember Hadoop sortable from back in your Hadoop days, you can essentially sort your data without having to deserialize and reserialize your data, which is pretty useful, right? Serialization is fairly expensive. Just checking, are there any heretics in the room that use Python or R? And I am one of those people sometimes. OK, there's 2. We should be friends, or at least keep the rest of them from murdering me. But for people that occasionally work in Python or non-JVM languages, data frames are incredibly useful because working with RDDs in non-JVM languages pays this really expensive serialization cost, and it's pretty ungodly. So yeah, why is Spark SQL good? And I'm going to get some coffee. Right, so Spark SQL is really good because it has this really efficient representation. It's also great because the cached representation gives us a columnar cached representation. So if we only need to work on subsets of our data at a time, we don't have to transfer huge amounts of it around. Another really awesome thing is the ability to push down operations to the data store level. And we can always do this when we're working with RDDs, but we have to do it ourselves and remember to do it ourselves. And that's a lot of work, and I'm pretty lazy. So if you load your data and then you immediately filter it, there's a good chance that the data store that you're reading from might actually be able to handle that filter more efficiently than Spark can. And with Spark SQL, we don't have to manually think through, is this a filter that I can push down or not? It'll just figure it out for us. And really, the more awesome thing that makes Spark SQL really fast is it can tell the difference between what we're asking it to do, right? In most of Spark, we're giving it arbitrary Scala lambda expressions. And right now, Spark just treats those as sort of arbitrary blobs and doesn't do any introspection on them. But with Spark SQL, we provide it with these typed SQL expressions, and it's actually able to look at them, figure out what the hell we're asking it to do, and do intelligent optimizations. And so how much faster can it be? It can be incredibly faster. If our baseline is groupByKey, pretty much everything is better than groupByKey, but that's like saying everything's better than a tire fire, so it's not a very high bar. But it's even better than reduceByKey, right? And reduceByKey is normally what we would replace a terribly written groupByKey piece of code with. Our data frame operation continues to be faster even once the JIT has had a chance to kick in and optimize our lambda expression. We can see it continues to be faster for future iterations. And this is because not only is the generated code really efficient, but our on-the-wire representation of our data is much smaller, so our shuffling and network costs are really low. But with every good thing, right, like all of this awesome performance, there has to be some catches, right? At some point, it's going to explode and bite us in places where we would rather not be bitten. And for Spark SQL, this is pretty much if you have an iterative algorithm, it's going to explode. It's not going to work very well. So if you're trying to do some machine learning on top of Spark SQL, you're going to have a bad time. There's some hacks that we can do, and I'll show one of them. Some pushdowns don't always work, and this is unfortunate. So while I said we don't have to think about it, occasionally we do have to think about which pushdowns we care about. And crazily enough, the default shuffle size is ridiculously small. It's 200 partitions, but it's OK. We can just bump that up. And if you're working in Spark, by now you've figured out that a lot of the default configuration values are not things for you. You want to be using something else. So the lineage explosion problem for when you're doing an iterative algorithm on top of data frames is really easy to fix. It's just kind of weird that we have to fix it this way. We can essentially round trip our data through an RDD, and then Spark SQL's optimizer just isn't able to go up above this, and it just looks at this RDD picture and tries to only optimize this smaller query plan. And this works really well. This is actually what's done inside of graph frames. Is anyone using graph frames? OK, cool. Well, if you were, this is how graph frames handle the large lineage problem with data frames inside of Spark. They just cut the lineage. And it means the optimizer can't do some certain awesome things, but it also means that our code actually runs, and that's probably more important. How many people are using the Dataset API? 3. OK, cool. So this is exciting. I really like Spark SQL. I like data frames. But part of the reason why I like Scala is I actually really like strongly typed languages. And data frames are just this blob of data, which has runtime type information, which is useful, but not why I like Scala, right? And datasets actually give me compile time type information, among many other things. But I think the compile time type information is really, really important. How many people enjoy writing user-defined functions for Hive? That is no one. And the first laugh, yay! OK, yeah, there was once someone that claimed to like it, but I think they were probably drunk. So datasets get us away from having to write user-defined functions, and they actually they let us write the code that we're used to writing. We can provide lambdas when we want to, and then we can provide SQL expressions when it's easier to write SQL. And we don't have to have this mental model of mixing the two. It just takes care of it for us. If you're working in Spark 1.6 right now, and because Spark 2.0 isn't out, you probably are, you will have to change your code if you start using datasets, because the API is changing for Spark 2.0. That being said, the API for pretty much everything is changing anyways for Spark 2.0, at least in small ways, so I don't think this is too big of a deal. So here's an example. Actually, let's just skip ahead to the annotated example of how to use a mixture of SQL-type expressions with functional type expressions. And this isn't super exciting. And there's an artifact here, because I actually wanted my example to compile in Spark 1.6, where I have to take my data set and turn it into a data frame and then back. But in Spark 2.0, we wouldn't have to actually go to a data frame and come back or specify what our type was there. It would just magically work, and we could intermix these two really nicely. We can also do functional style maps. And now we've got Boo again, who is not David Hasselhoff, but is very cute. So we can intermix functional style maps, and the dataset types work out for us, right? We're taking in a dataset of this case class called raw panda, and I'm doing some random arbitrary lambda function, and I'm getting back a dataset of doubles. And this is really cool because I get all of the really awesome bits of Spark SQL without having to sort of constrict myself to SQL expressions, right? Because I don't really like writing SQL expressions compared to writing lambda functions. I'm actually pretty bad with SQL, so I really like this. So switching gears entirely, let's look a bit at how to validate our Spark jobs. Everyone here already tests their Spark jobs, right? Is there anyone in the room who doesn't test their Spark jobs? Good. OK. Is there anyone in the room that doesn't validate their Spark jobs? OK, at least 2 people. How many people in the room don't know what I'm saying when I'm saying validate your Spark jobs? Hey! OK, there we go. That's more what I was expecting. OK. Lovely, lovely. I need some coffee. So we're all good software people, right? We know we should test our code. And we also know that our tests aren't always enough, right? Because we can have our entire test suite pass, and we actually just produce garbage results, right? Now, hopefully, our tests catch everything, but there's a good chance that your tests aren't able to cover all of the myriad of ways that the real world is able to fuck shit up. It is just ridiculous, the kinds of things that will show up in your data, right? You'll have names which are somehow encoded as the string null. You'll have like just all sorts of random crazy stuff. And it will change, right? Your upstream data providers, they're giving you data in one format today, and tomorrow they might just drop a field or rename a field, or even worse, repurpose a field, right? They might decide, well, we had this field for the user's income, but I'm gonna change it to some sort of categorical data. And your tests aren't going to be able to catch all of the things that are going to change in the real world. So I think it's really important to introspect our Spark jobs while they're running to try and figure out if they're performing reasonably, so that when our Spark job is done, we actually know if we can trust the results that it's produced, right? Because it's way better to not push out a new recommendation model than it is to push out a recommendation model that recommends hugely inappropriate things to people. And I say this as someone that has pushed out a recommendation model that has recommended hugely inappropriate things to people. That was a really terrible 2 a.m. phone call. I don't want to have another one of those. It's not good. And my tests weren't going to be able to catch that. So there's a whole bunch of things we can do to sort of validate our Spark jobs. We can validate if we're having to drop records, especially if you're working with JSON data. There's a good chance that some of your records aren't going to match whatever schema you were expecting, and you need to drop some of them. And that's not the end of the world, right? You don't want to stop your program just because you encountered one invalid record. But if you encountered like 90% invalid records, there's a good chance you really don't want to continue, and something has gone pretty wrong. If your job normally takes an hour to run, and it completed in 20 minutes today, I mean, either you upgraded your cluster or something has gone kind of wrong. And you should probably double check before you deploy your model to production and start like trading on the stock market with it. So there's a lot of really easy, simple rules we can write, right? We can say like my execution time should be similar to my execution time over the past year. We can say that the number of users should be monotonically increasing, or if we're at a company that isn't doing so well, the number of users should not be decreasing by more than 50% per day. And if it is, I'm going to be interviewing anyways, so it doesn't matter. Yeah. So we can use accumulators to encode some of this information. It's a pretty convenient way of keeping track of sort of incidental things inside of your transformations, right? You don't want to always return an option from everything to indicate the potential of a failed record and count at each stage, but you do want to get an idea of, if you've encountered an exceptional state. The problem is accumulators are kind of flaky, and it's mostly the interplay between caching and node failures where it can get really, really funky. But if you use relative rules, it's pretty OK. So because it generally tends to need to recompute a chunk of data at a time. But essentially, don't write rules that are like, if I encounter 1,000 records that are invalid, stop. That's not a good rule. Write a job that says, if more than K% of my data is invalid, stop. Because it might accidentally recompute some of your data several times. So this is a really simple example where we create 2 accumulators, and we keep track of the number of things that we're throwing out. And we say, if bad.value is higher than 10% of our OK value, stop. We don't want to use our results in production. If you think this is cool, there's an early stage project to make it easier to write these rules, especially the ones that look at historic data, so how your job's performed in the past year or 6 months or whatever. But it's very early stage, and you shouldn't use it in production. But I think it can be kind of a neat project. And I also have a PR out in Spark to try and make accumulators reasonable, so we don't have to limit ourselves to these relative rules. It's Spark PR 11105, and the JIRA is 12469, if anyone happens to be sort of interested in seeing why accumulators behave kind of weird and what we can do about this. These are two little things. So for now, some of the most common validation rules that people use on their jobs are just checking the file sizes of their outputs, checking the execution time, checking the file sizes of their inputs, the number of records read. These are all internal counters that Spark keeps track of that we can access. And the Spark validator package shows you how to do this if you're so inclined. But you shouldn't actually use the validator package. You should just look at it and copy the parts of it you want. And yeah, so here's an example of using the validator package. It's a thing. On a personal note, I think it's okay to have validation rules that sometimes misfire. Just like don't throw away the data, just keep it and don't push it to production so you can investigate what's gone on and then manually figure out if it's okay and if it's a reasonable time to add an exception. Maybe your company did something terrible and you lost half your users yesterday, so this is actually expected that your job processing time went down. How am I doing on time? Oh, cool. I don't have a lot of time. How many people really care about, actually everyone was already testing their Spark code, right? Everyone promises me that they were already testing their Spark code? Okay, lovely. Let's see if this, oh, damn it, stupid Google. Okay, yeah. If anyone really cares about testing, it'll be in the slides, and I would love to chat with people about testing. Especially, there's some really cool stuff. Everyone here knows about Scala check, right? Yes? Okay, good. If you don't know about Scala check, come talk to me. It's awesome. You should be using it with Spark. It's really cool. But let's go ahead and sort of just wrap up and do some questions. If you care about testing, there's a bunch of really cool libraries. I have a talk on YouTube. I should have put the link in there. It's more focused on testing Spark, and there's some blog posts. There's a bunch of really good Spark resources. I think the programming guide is often overlooked. A lot of people seem to just work with their IDE and look at what it's tab completing to. But if you actually read the API descriptions, it'll give you an idea of what things are going to give you really terrible performance, like groupByKey, or things which implicitly collect some of the data back to the driver. So I think it's worth taking the time to read the docs for the things you're using. Kay has some really interesting research for more researchy people about sort of figuring out Spark performance stuff in general and where those things are. I'm also going to try and do an online office hours where you can bring your Spark questions and I'll answer them. And you can follow me on Twitter and I'll tweet about them once I have a chance to sit down in the same city for a period of greater than 48 hours. Cool. Oh yeah, there's some books. You should buy them. Don't buy the out-of-date one. It's not very good anyways. I wrote it, and I'm telling you not to buy it. So really, yeah, don't buy the first edition of Fast Data Processing with Spark. If you want to buy any of these other books, that's cool. And I get money from some of these books, so it's very cool, and you should buy several copies. Especially if you happen to have a corporate expense account, I recommend High Performance Spark as the gift of the season. Your dog wants one, as does your cat, and your car could also use a copy. Right now it's PDF only, but you can still buy several PDFs, I promise. It's an early release. We'll be adding more chapters as we go. It's focused on making high-performance Spark applications, so helping you go from sort of just understanding the API at its basics to how to make stuff go fast. If you don't want to buy the early release and you just want to give me your email address to spam or selectively contact, I will let you know when it's done. And if you go to highperformancespark.com I'll send out an email when everything's ready. There's a bunch of cool Spark videos, but you all probably already know this, so we'll skip that, and we'll do questions. For the 2 heretics in the audience that use Python, please get in touch with me. I'm trying to do some crazy shit with Python in Spark. I'm sorry, everyone else. I've gone partially to the dark side, but they had cookies, so it was really hard to resist. But give me your PySpark UDFs, and I'll try and make them run fast. And if you care about software testing and you don't hate surveys, I would love to hear your feedback on what you're doing to test your Spark applications so that I can make better libraries for testing Spark applications. And now we'll just do some questions until people come and kick us out of this room. It looks like no one really likes that question link thing, so we'll just do hands up questions. And you can get this book. It's a book made of paper, as opposed to PDF. Come on, someone's got to, okay, yeah.
Awesome, thank you for your talk. The question is, can we benefit from using external shuffle service? If we do, does it mean that all the RDD is going to be deserialized before going to external shuffle service, and will it be more performant if, compared to usual shuffle?
So the external shuffle service is fast. If you're working with Spark SQL, actually, your data type doesn't need to be deserialized to do a sort on, because the data is actually just sortable directly. So it depends sort of actually what your data is, how it's going to behave with the external shuffle service. But yeah, you probably want to be using it. And you get a book.
Awesome.
And I don't have any more prizes. I might. Let me see here. What's in my backpack? Does anyone really like, okay. If anyone really likes Hello Kitty, I have some Hello Kitty buttons. If no one likes Hello Kitty, I'm keeping these for myself. But if anyone likes Hello Kitty and wants to ask a second question, I can give you these limited edition, well, probably not actually limited edition. I can give you these mass-produced San Francisco Hello Kitty buttons. Or, no, okay, no more questions. Okay, cool. Thank you all for coming. You've been wonderful. I'm sorry there wasn't as much David Hasselhoff as I had planned. Next time I will add more. Thank you.